Okay, 9.3. We're going to start with just the integral test, and then you can practice that homework. 9.3, 3 through 31 odd. Once you finish that, come back and you'll see the video for the second half of 9.3, which is P series. Very, very important stuff. So let's tackle the integral test. You don't use it very often, but when you do need it, it's the only thing that works. So you have to learn it and learn it well. Now, what we're doing in this chapter is we're learning a bunch of different ways to test a series to see whether or not it converges. Some of them we can find the sum, the actual answer. But for most of them, all we can do is determine whether it is convergent or not. On the test for this part, I am going to be very, very picky. You have to tell me all of the components of the test. You have to prove all of the premises, and then you have to show me how you applied the test. And you have to tell me what test you're using. You can't just write down a bunch of stuff and then say it's convergent or it's divergent. So for this particular test, if you've got an a sub n that is some function of your counter, then the integral test says, consider, this is the way I say it anyway, consider f of x. This is the same f that we stated before. If f of x is positive, continuous, no asymptotes or anything on your interval, continuous, and this is the hard one, decreasing. In other words, it's positive and it's always getting smaller. So obviously it's going to go to 0, right? If something is always positive and it's always decreasing, then you're bounded below by some positive number. If it's always whatever. Here we go. Then if you can take the integral, now the integral test says a 1 at the bottom, to infinity, integrate that function. If it's continuous, or if it converges, sorry, then the series converges. And the opposite is also true. If the infinite series of a, sorry, back up. It's just like class, isn't it? If the integral to infinity of the function diverges, in other words, it blows up to plus or minus infinity, then so does the sum. So, if the integral converges, then the series converges, and if the integral diverges, so does the sum. Now, when you are doing this test, you have to prove the premises. You have to show me that it's always positive, that it's continuous, and show that it's decreasing. In other words, the next term is always less than the current term. And I'll show you some examples of how to do that. All right? You have to prove those 3 things first. Then you take the integral. Remember, your limit is infinity. You've been practicing limits at infinity if you've been doing your homework. If you get a number, then your series converges. If you get infinity, then your series diverges as well. Got it? Okay, now these only tell, this test only tells convergence or divergence. Not sums. Okay, in the last section, we learned about the geometric series, and if you're multiplying by a number smaller than 1 every time, you can actually find the sum. If you're multiplying by a number bigger than 1, then it diverges. And then the other one was the telescoping series, and we practiced finding those sums as well. So in this case, all you can find is convergence or divergence. You cannot find sums. So let's do some practice. What if we have a sub n equals 1 over n squared plus 1? So if we're going to use the integral test to prove this, first we have to say, is it positive? First off. Now, what about 1 over n squared plus 1? Is it positive for every value of n from 1 to infinity? Yeah, because n squared is always a positive number, and you're adding more to it. So the bottom's always positive, the top is always positive. So that a sub n is always positive. Is it continuous? I'll spell it right this time. Is it continuous? Well, there's no asymptotes because n squared is always positive, and you're adding 1 to it. So there are no asymptotes, and it is continuous. So check. Is it decreasing though? Let's look at a way to do this. Now, I gave you an example in the homework examples last time. I just didn't say anything about it because I didn't speak. So what I want you to do when you're trying to figure out if something is increasing or decreasing forever and always, amen, is compare it. That's a circle. We're going to fill in the circle in a second. Compare your a sub n to the next guy. Now, square that out. You're going to get n squared 2n plus 1, and you get this guy. So this is what we're comparing here. N squared plus 1 and 1 over n squared plus 2n plus 2. Now, we've already talked about the fact that this is always positive, and this is always positive as well. Think about it. Think about it. Yes, it's always positive. If you set this equal to 0 and solve for n, what would you get? Let's just do this just for good measure here. N squared plus 2n plus 2. Say can't factor it. So I'm going to move that 2 over here. I'm going to take half of this 2, square it, and add it to both sides. This is going to give me a perfect square on the left and a negative number on the right. When I take the square root of both sides, I'm going to get an imaginary number. So this thing never equals 0, and it's always positive. Okay? So that was my little thought bubble there. Prove that it's always positive. So how are you going to solve this little situation though? Well, if they're both positive, the reason that we did this is that we can multiply both sides of our inequality by the common denominator, which is this times this. So when we multiply by the common denominator, if they're both positive, the symbol in the middle won't flip. So we get, oops, sorry, hold the phone. All right, so we get n squared, did it again. Okay, black. N squared plus 2n plus 2 compared to n squared plus 1. Well, let's subtract n squared from both sides. Why don't we subtract 2 from both sides? Now, n starts at 1. So this guy is always at least 2. Even if n started at 0, it wouldn't matter because that guy's negative. So we see that we're pointing that way. Now, what does that mean for the integral test? Well, if this guy right here, if the a sub n plus 1, this is what we showed. We showed that a sub n is bigger than a n plus 1. Therefore, no matter what n is, the next term is less than the previous one. So this thing is always decreasing. Check. Okay, all of that work, and we haven't even done the integral test yet. We've just laid the groundwork to know that we can. So we're going to integrate from 1 to infinity, 1 over n squared plus 1. Oh, make that an x. Dx. Well, that's an arctan. Arctan x over 1 from 1 to infinity. Oh, I know you guys love this so much. We have to plug in the infinity. Where is the arctangent infinite? Or where is the tangent infinite? Well, the tangent is the sine over the cosine. And for this to be positive, it has to be in quadrant 1 because that's positive infinity there. And for it to be positive infinity, the denominator has to be 0. Where in this area are you approaching 0 in the denominator? Right there. So we get pi over 2. Minus. Now, where is the tangent equal to 1? Well, tangent sine over cosine. Where do the sine and the cosine equal each other? Right there at pi over 4. We get a number, pi over 4. That is not the sum it is just a constant. We showed that the integral converged to a value. Therefore, my infinite series, there we go. Therefore, the series from 1 to infinity of 1 over n squared plus 1 converges. Why does it converge? How do we know that? Because the integral converged to a number. And that's the integral test. Now I said that previous problem, once we get into comparison tests, you'll be able to use a p-series, which we're about to learn about in the next video, and a comparison test to show that that converged. But some problems you have to use an integral test. We just don't have any other way to do it. So a sub n, let's say, is the ln of n over n for n equals 2, 3, dot, dot, dot. Now, I hope you're reading your book. There's a note at the bottom of page 609 that points out that even though the integral set test said that you had to integrate from 1 to infinity, it still works no matter where you start. Pick any number, it's going to be smaller than infinity. You start the integral at that number, and if it works, it works. Sometimes these series, not this one, but sometimes the series will pop around and then settle down. Did you see what I did there? So you just have to get out past the counter where things start to settle down and you're good to go. So when we do the integral test, if we can, we're going to use this as our bottom limit. Got it? Good. So what are the three conditions that we have to prove? Is it positive? Well, we're plugging in a 2 to begin with. What is the ln of 2? Sorry. What is the ln of 2? Well, e to the what equals 2? E is 2.71 dot dot dot. So that exponent has to be smaller. I'm sorry. It has to be positive. Okay? It's smaller than 1. It's a root. You have to take some root of e to make it smaller than itself, but it's definitely not a negative number. So that was my thought bubble. So we see that it's positive, and is it continuous? Well, the ln is not defined for 0 or a negative, but we're starting at 2, so we're good to go. We can't divide by 0, but 0 is not one of the options, so yes, it's continuous. The best way to find whether something's continuous is to figure out if it's where it's discontinuous, right? So there you go. What's the next question? Is it decreasing? This is the hard one, right? Well, another way to tell if a function is decreasing is just to simply take its derivative. If the derivative is negative for all values of n or x from 2 to infinity, then our series will be decreasing as well. So let's look at f of x. The ln of x over x. F prime of x is going to be the bottom, derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. Make it pretty. Now, is that positive or negative for x greater than or equal to 2? Well, let's think about this. The bottom's always positive, right? 1 minus the ln of x. Where does this equal 0 first off? And this will equal 0. Let's do a little thought bubble right here. The ln of x equals 1 for x equals e, which is greater than 2. So what we need to do is to go back and make this say, remember the note on page 609, doesn't matter where you start, and remember that n is an integer, so we can say for x greater than 2, because once x gets to be 3, or n is 3, This top is definitely a negative number, which means that it will be decreasing. Okay. To perform the test itself, we're going to integrate now from 2 to infinity. Because of the rule at the bottom of 609, we can do that. We're integrating the ln of x over x dx. How the heck are you going to do that, huh? Well, remember that the derivative of the ln of x is 1 over x. So we look at this integral as the ln of x times 1 over x dx. And we have u du. It's a simple power rule. So, here we go. We have blob squared over 2 from 2 to infinity. We plug in the infinity, and what do we get? We get infinity. This series diverges. Now you try the homework for this part. I think it was 3 through 31.